To extract gold from raw ore, the metallurgical industry relies on a single chemical process, cyanidation. When implementing this process at scale, engineers divide it into two primary physical applications based on the ore type: heap leaching for massive piles of low-grade rock, and tank leaching for contained, controlled processing. Looking directly at this branching logic tree, we can see the subdivisions of cyanidation. Following the path through the tank application, the methodology splits again into two distinct branches: agitation and percolation. Agitation relies on heavy machinery to constantly stir the ore and solvent together. It consumes a tremendous amount of energy, but it delivers rapid extraction and high absolute yields. Percolation takes the opposite approach. It is a passive, gravity-driven method where a liquid solvent slowly trickles down through a static bed of rock, requiring almost no kinetic energy to operate. Choosing percolation means accepting a deliberate engineering trade-off. The operation sacrifices extraction speed, often taking days rather than hours to process a batch, in order to strip away mechanical complexity. It also accepts a lower overall gold recovery rate. In exchange, the facility completely bypasses the massive electricity costs required to keep thousands of tons of heavy slurry in constant motion. Capital expenditures drop significantly as well. The passive nature of the workflow removes the need to purchase, maintain, or power expensive industrial concentrators and complex filtration systems. This specific profile makes the method highly viable for distinct targets: loosely packed alluvial sand, porous low-grade ores, metallurgical slag, and smaller-scale mining operations that lack vast capital backing. By evaluating these factors, we see that percolation cyanidation operates exactly as intended. It is a strictly structured system built to prioritize low overhead and energy efficiency over chasing every last ounce of gold. Before introducing any chemical solvent into a percolation tank, the raw material must pass strict physical parameters. The rock itself must be crushed down to a maximum particle size of strictly -10 millimeters. Beyond sheer size, the internal composition of the ore bed needs to maintain a naturally loose and porous structure. Alluvial sand from riverbeds and highly porous metallurgical slag left over from smelting provide the ideal physical geometry for this process. If the void spaces between these particles become blocked, the system experiences its primary mechanical failure mode, occlusion. This microscopic view illustrates the danger. When clay or slimes are present, they pack into the narrow gaps within the rocky matrix, causing the downward flow of gravity-driven solvent to come to a complete physical halt. To prevent this blockage, engineers enforce a rigid prerequisite. All mud and slime must be thoroughly washed and separated from the main ore body before tank loading begins. Those separated fine materials are not discarded. They are simply redirected to an agitation cyanidation circuit, where their small size is actually an advantage. Back at the primary percolation pool, only the optimally sized, clean rock is loaded into the vat. Without this careful sorting, the solvent cannot reach the target metal. In this model, consistent mechanical permeability acts as the absolute threshold for extraction success, superseding even the chemical reactivity of the cyanide itself. With the porous bed established, the chemical phase begins by applying a cyanide solvent evenly across the top surface of the ore. This 3D cross-section tracks the fluid dynamics inside the tank. Gravity pulls the solvent slowly downward through the open channels of the rock matrix. As the liquid makes contact with the ore bed, the cyanide chemical immediately dissolves the exposed gold particles. The descending fluid gradually saturates with the target metal, creating what metallurgists call the pregnant liquid. Capturing this fluid without letting the crushed rock collapse and plug the drain requires specific structural engineering. Examining the lower quadrant of the tank, we find a specialized filter layer suspended above the true structural floor. This is the false bottom. The permeable filter allows the dense pregnant liquid to drip through unimpeded, while safely supporting the solid ore bed above. The saturated fluid finishes its descent, pooling in the empty cavity below the false bottom, separated from the rock. An outflow pipe taps directly into the side wall of this void. Positioned exactly between the structural floor and the suspended filter, it drains the gathered fluid outward without ever disturbing the stationary ore bed above. Once the primary cyanide solvent has fully drained through the system, a secondary wash phase begins. Operators flush clean water down through the same porous channels to rinse away and capture any valuable pregnant liquid that remains clinging to the rock via capillary action. With the solvent and gold entirely flushed, the remaining barren rock, now classified as tailings, is excavated from the tank using manual labor or mechanical scrapers. Emptying the vat acts as a reset, immediately preparing the physical space to accept the next incoming batch of raw crushed ore. The integration of the false bottom is a highly effective design choice. It allows continuous, passive separation of valuable liquids from solid mass, achieving isolation without spending a single watt of energy to move the rock. With the pregnant liquid successfully exiting the tank's drain pipe, the fluid routes outward into the secondary processing circuit. The fluid flows directly into the next critical piece of hardware, a displacement precipitating device. Inside this unit, a chemical reaction forces the dissolved gold to drop out of the solution, precipitating into solid form so it can be physically collected and permanently removed from the fluid stream. Having surrendered its gold, the solution loses its pregnant status. It exits the precipitator as what metallurgists define as a lean liquid. Rather than being discarded, this stripped liquid travels onward to a dedicated holding pool designed for solvent regeneration. Looking at the process mapped out on this flowchart, we see the lean liquid arrive at the holding pool, where operators inject a precisely calculated dose of fresh cyanide. Because the fluid still retains a base level of its original chemistry, this targeted injection is all it takes to spike the concentration back to optimal leaching strength. The fully restored solvent is then pumped straight back to the top of the initial tank, ready to cascade over the next batch of raw ore. This closed-loop chemical cycle ensures continuous recycling of the core solvent. By retaining the liquid and only topping up the degraded chemistry, the operation tightly controls external material costs, ensuring the economic viability of the entire percolation setup. Operating a percolation cyanidation facility demands two substantial commitments. It requires a massive spatial footprint for the sprawling tanks and an exceptionally long working duration to process each batch of ore. However, those structural costs are strategically offset by profound operational savings. The design effectively zeroes out the need for complex mechanical agitation and slashes electrical demands across the board. The simplicity of this engineering framework provides an additional, highly relevant benefit: strict architectural adaptability. If we refer back to our chemical loop diagram, notice how modern operations can seamlessly swap out highly toxic traditional cyanide for environmentally friendly alternatives like JIN CHAN. Because the physical mechanics of the flow remain identical, substituting the chemical agent requires absolutely zero structural modifications to the existing tanks, the suspended false bottoms, or the downstream precipitators. Facilities can update their environmental safety standards overnight, mitigating severe chemical risks while preserving every energy and equipment cost advantage the system affords. Ultimately, percolation cyanidation proves that absolute maximum yield is not always the target in metallurgical extraction. True engineering elegance lies in identifying the constraints of a project and building a system that deliberately prioritizes mechanical simplicity, extreme energy efficiency, and long-term operational adaptability.